Started. Okay, well, welcome to our lovely new room. Again, I'm Dr. Paul West. Actually, has anyone not had me before? Okay, a couple people. All right. Architecture. Oh, cybersecurity?
Yeah.
Okay. Yeah, it's going to be rough.
Okay.
Just warning you right now. It's going to be a rough course. So, I'm Dr. Paul West. This is computer architecture. The idea, or there are many things we're going to need to. There are many reasons for this course, but architecture is going to talk about how the computer is assembled from a very low level. How do we on hardware actually assemble the computer, put it together to actually produce a machine that can run our software. From the computer science students in here, this is very important, so you will have a good basis about why certain errors occur, like segmentation fault, why memory behaves the way it does, why all of a sudden programs just perform terribly even though you're using a really great algorithm, as well as a couple other things. On the security side, this is very important because due to how architecture has evolved, there are certain very important security aspects that you'll need to be aware of. And classic example that just came out, was it 2 or 3 years ago, was Meltdown Inspector, which is a pure hardware issue due to how architecture, how the cache system was developed, how our out-of-order processors were developed. Because of those two, a meltdown occurred in Intel, which basically allows any user to just read the entire program space, so they can just read your passwords without a problem. Spectre is similar, except for it's a lot harder to do. But the nice thing about Spectre is it works on any out-of-order processor that uses a cache system. But it is very difficult. And there's, of course, a lot of other security issues as well. So for both of y'all, while your objectives from this course will be a little different, it's the same material. I know that cybersecurity, you are not programmers, but you are going to have to sit down and at least do some Verilog and some assembly for you to actually learn how this is done. I mean, y'all have taken procedural and probably OOP as well, so you know at least the basics of programming. So that's the idea, or high level, what's going to happen in this course. As I told, cybersecurity, unfortunately, it's going to be your hardest one because you're going to have to really delve down low level, even though most of the time you're concerned about vulnerabilities. Now you're actually going to have to really figure out how the machine is put together. Also, this is a bit of an engineering course. This is also the last semester that discrete math is not a prereq, which I'm guessing is why a lot of people are here. Is that the case? Okay. I understand where you're coming from, but I do believe that once discrete math is a prereq, a lot of things I teach here are going to be a lot easier to explain, because really your processor is just a push-down automaton. If you're taking discrete math, you've already done a finite state automaton, so push-down is just the finite state with the stack. Once you have that down, we can just prove and do everything else. The whole architecture is going to make a lot more sense. Unfortunately, we're just going to have to do it the hard way, which is fine for this class. All right. So overview, computers are one of the more complex devices humans have created, yet they're very simple. What's going to be interesting, especially at the beginning of this course, is there are different ways to evaluate what a computer is. For example, you could just think of a computer as a bunch of silicon with some arsenic put in there, and you're done. That's all we have. Of course, that's not too useful. There's a couple other things that we're doing, but on the basic level, if you just had a machine that could put arsenic in the right spots on top of silicon lattice, you're done. We're good. Maybe some gallium as well, just to change it up and get some diodes. But besides that, you're done. Of course, we'll look at other aspects as well. Basically, and we are going to look at the transistor level, at least at one point. A bunch of transistors etched in silicon. And by a bunch, I definitely mean billions. Usually they give you a transistor count when you look online. And I would love to go online and show you what all these counts are, but apparently I am not allowed to. But I remember the latest ones were definitely in the billions of transistors. So real quickly, can a team of humans feasibly just etch together a billion transistors one at a time and have new processors come out every 6 months? No. We have a lot of computer programs. What's that?
It'd be pretty cool if we could.
It'd be pretty cool if we could. I mean, in the beginning, that's what they did. Of course, you only had, I think it was 1,700 transistors. A team of people can do that. We got that. We can do that. Actually, one person, if you sat down for months straight, could probably do that. But yeah, we have a lot of programs that help, and we're actually going to use some of those programs in this class. Another thing is, how do we go from C to execution? You all have not done assembly, but high level, the computer or your compiler just translates your C into assembly, and then an assembler translates your assembly into actual machine code for your computer. So we need to go in depth. How does your program or a compiler, the code, take your code and transform it into something the computer can actually execute? Because the computer does not speak C or Java or whatever. You need a translator, which is what a compiler is. It's just a translator. So we'll explore more of these in depth. Let's see, logic. So we'll have to look about the different instructions that are used to execute this. I have been asked to convert to x86. I'm going to repeat myself here, but please keep in mind that this is the first course where I'm going to teach x86. All the documentation is in MIPS, so if something looks like it's not x86, please tell me, and I'll go ahead and look into it. Obviously, if you have an error, give it a good try before you come contact me, but be aware that unfortunately I'm having to convert all this from MIPS to x86, so I'm going to forget something, that's all. But we need to take these instructions, take these signals in general, and execute them in steps. These are what's called a clock cycle. We'll get to that later, of course. And our job is to see how this is done and give you an idea of how computers can be built to do all our computations. All right. So, still no interwebs. Maybe, well, that didn't work. Maybe we can try the Apple software. Let's see what that does. Not registered. Let's disconnect there. Not connected. Great. Let's connect here. No luck. We'll try that one again. All right. Computer revolution. All right. So this is underpinned by Moore's law. Does anyone know what Moore's law is? With the overhead right behind your head, Brian, it looks like you're raising your hand at all times. I just thought you raised your hand again. All right, so Moore's law. Moore's law has unfortunately been misrepresented a lot. It's basically the density of your computing chips doubles every 18 to 24 months. So that's the density, aka how many transistors you can pack inside an area doubles every 18 to 24 months. That does not mean that your processor necessarily goes twice as fast. It just means now you have twice as much space to utilize to build your processor every 18 to 24 months. This law is interesting because we keep thinking we're about ready to break it, and we don't. We thought it'd be well broken by now, and there's no way we could hit the law, still make these transistors smaller. But it looks like at least for the next 10 years, possibly 20, this law will still hold. After that, we don't know, but I'll tell you right now, that has been the story the entire time that Moore's law has existed. We know about the next 10 years. At one point, we only knew about the next 5. But after that, we don't know what's going to happen. Although most people are recognizing we're about ready to hit a wall because, was it 7 nanometers is what AMD came out, and the width of an atom, I think it's like 0.3. So we're going to hit a wall soon about how many. You can't, unless we figure out how to start splitting atoms, which, well, we figured that out, but you don't want to be doing that. How about that? So, what's that?
So I thought the issue is when you get too small, the electrons start to jump over and don't stay where they're supposed to.
There are many, many challenges as the package size shrinks. There were other challenges that came along as well. But to me, the wall that everyone sees is like, well, at some point, everything's the size of an atom, and then you want to chop up an atom.
It's quantum computing.
What's that?
It's quantum.
It's computing. I should do a little lecture on quantum computing. Businesses love to sell you all things. All right, we need to make novel applications feasible. So there used to not be computers in automobiles. Obviously, all our cars nowadays have computers, actually very sophisticated ones that control the fuel mixture into your combustion chamber. Cell phones, you're of course used to that. Human Genome Project, which I think finally completed. Hey, the World Wide Web, y'all heard of that one, right? Yeah. No, I knew it. Well, the point here is computers are pretty pervasive. I mean, you have what is it? Can't believe I forgot it. There's some medical equipment as well that is definitely computer-based. All right, classes, there's personal computers. Those are the ones that stand on your machine or in front of you, and servers, computers as well. It is important to distinguish between the two because I'll ask you, what is usually the difference between these computers? Your PC versus a server machine. Y'all got this. You got okay, yeah?
Yeah. Well, usually servers got a different OS. It's like similar to like a regular, but they have a lot less like bogged down resources, like GUI looking nice, and they're usually
Okay, so a
more
lot of
set up
servers are
for-
headless.
Yeah, but then they're set up more for dealing with a lot of like client network handling. There's a lot more network traffic. going
Network
on.
traffic. So they probably have more higher end network cards,
Yeah,
right?
bigger hard drives.
Now, from a processor perspective, what would be more important on the processor level for a server as opposed to a personal computer? I know this is a hard question, but let's see if we can answer it. Hmm?
Don't like really big servers have like tons of like cores on them. Don't like,
Right. Why would they have a lot of cores
they do lots of stuff at once.
at once? And why wouldn't you want that, or why do you, on your personal computer, you don't care about having 40 cores and sitting in front of you?
Because one person can only do so much at the same time.
All right. So that is a huge architecture difference. Server machines usually have many cores, and while a personal computer usually has few cores. Also, there's another interesting aspect, or at least interesting to me. In a personal computer, when one person's using it and they click, they're more interested in how fast they can get a return. While a server machine is more concerned about how many connections it can handle at the same time. Now, this is a very important difference to start understanding, especially early on, because this is going to affect a lot of things. So the personal computer they care more about latency. They click, they want something to come back. Server machines are more about throughput. In other words, if it takes them, a quarter of a second or half a second to service everyone, but they can service, 200 connections, that's better than only servicing 50 connections that respond in 0.1 time or 0.2 seconds. While a personal computer, if it takes a quarter of a second every time you click to do anything, that user is going to get really annoyed really fast. So the architecture is actually going to be different. The architecture for a personal computer will be geared towards quick response time, not high throughput, while the server machine, they can sacrifice some latency in order to be able to handle more at once. Because on a server machine, the other aspect is power. Because Google's, what they call server, what do they call it? I can't believe it. Server centers, there we go. One of their biggest problems is how much power these things take. They consume a lot of energy, electricity, which of course equals money. So if you can figure out ways to tone down your processor to consume less power but still service the same number of connections and not really care too much about latency, that saves Google a lot of money. While the personal computers, most of the time people don't care about how much power they take, I've learned. They just want it to respond really fast. So that's how it is. So supercomputers will be another one. I really wish we could go to top 500 right now. I'm going to have to figure out what the problem is at some point. Maybe it'll connect, maybe not. But the top 500 will list the top 500 supercomputers around the world. And last I checked, I think the US took #1. Are you checking for me, Mickey?
I closed my computer, so now I have to reconnect.
Oh, this seems so familiar.
Wait, here we go. The list. What am I looking for? On
Top 500.
Or-
There should be an index. Let's see what we got.
Is the one on the right?
Scroll top. Lists. Top 500, November 2019. Boom. Go down. What's #1? Summit. IBM.
United States.
Ooh, oh,
Yeah,
number
number
2.
two.
Oh, nice. So what chips are in that one? Are those the PowerPC ones?
#1 is Summit IBM Power System AC922.
Probably dual InfiniBand with some type of GPU.
Dual Rail Mellanox EDR InfiniBand.
Wow. Okay.
These are
Yes.
There's 2.4 million cores.
2.4 million cores. So this.
It only takes 10,000 kilowatts of power.
I know.
Not too bad.
I mean, that's just a power plant, right? Well, go down to the first Chinese one, because this is where it
The
gets
first
interesting.
Chinese one has 10.5 million cores.
Okay,
and
hold on.
poles.
So remember that the U.S. is 2.4 cores. The Chinese one is 10.5, 10.5 cores. How much power does the Chinese one take up?
Just over 15,000 kilowatts.
Yeah, so it consumes more power, but how much? What's its? Is it in T-flops right now?
Yeah, T-flops.
So T-flops is trillion floating point operations per second. It's just a way to measure how much, I guess, computational power it has.
So the
America?
I don't know what the difference between Rmax and Rpeak is.
So Rmax is the realized max, and the peak is more of a theoretical, what it could bounce up to. So let's go with Rmax for now.
And the max for the number one United States one is 150,000,
Okay.
and the one in China is 93,000.
So there you go. So that's what, now think about that. That's interesting because the Chinese one has more cores, consumes more power, which makes sense because it has more cores, but its processing is less than the US one, which has fewer cores, like 1/5 the number of cores almost, consumes, it's about 66% of the power, yet has not quite double, but we'll say 70% more processing power. So there is a lot of room, or hopefully you can see there's a lot of competition about making processors as efficient as possible. And I think the Chinese one uses the Chinese processors like the Sun something or another.
Sunway.
Sunway, yeah, the Sunway, yeah. So, and the PowerPC is a special chip as well. It's not the ones that usually run in your machines. All right. Why do we have supercomputers? High-end scientific and engineering calculations. Oh, I didn't put the bullet point of trying to break security all over the world, but that is another one as well. The DoD has their own machines that they try and do that. Unfortunately, highest capability, but a very small fraction of the overall market. All these machines are very custom built, and they're usually very pricey, and there's not too many of them. And usually they get shut down fairly quickly. But here's a list. On the other hand, well, so hopefully on a supercomputer you can tell that in general we don't care too much about power. It's more about how much computation can we get done. On the other hand, embedded, so these are like on your phones. So on your phone, what are you more concerned about than maybe with a supercomputer, your PC, or a server? The pictures of cats.
You want to be able to.
How about your battery life?
That's
Yeah.
true. Yeah.
Yeah. So you're very concerned about power.
Yeah, because if your power goes out, you can't send pictures of cats to people.
Right. So your phone's power or utilization of power is incredibly important. So sometimes on a phone, and by sometimes I mean almost every time, they will sacrifice latency or throughput just to extend your battery life. Of course, they have to find a happy medium because people still want their phones to respond very quickly. You don't need a lot of cores because that consumes more power, and again, you're trying to lower the power usage. So on embedded systems, you're going to use a lower power chip, which is going to be slower and fewer cores. That's why a lot of your phones are using ARM processors, because those are definitely geared towards low power, I guess, performance. All right, great. I used to, let me show you, let me first explain this graph, and then we'll try and derive what's going on. So this blue line are your desktop, basically market share, and there is no date on the bottom. That's terrible. Well, it starts in 2009 and ends in 2019. And what's the green one is your mobile, aka your phones. Your purple is your tablet, and your red are your consoles, aka PlayStation 3, PlayStation 4, et cetera, et cetera. So, unfortunately, consoles are way down there. But
it's like slightly more than 0%.
yeah, it's like
It's
0.02
like
or something. It's something. So for a long time, it looked like this. This is where it stopped. And so we were all predicting that the mobile market was going to overtake the desktop. But as you see, interestingly enough, they basically evened out. So for a while here, I was teaching a class thinking that your phone was going to overtake and no one's going to use a PC, the next 20 years. But it looks like everyone's going to continue to use a PC, which is good because I definitely prefer those over my phone. And I bet you it's just going to bounce around a lot about usage. Probably because if you have a phone, you still need to use a PC in order to sync up and do different
Are
things.
they counting like a laptop?
Yeah.
As a desktop.
Yeah.
So they're saying mobile, literally like a cell phone.
A cell
type
phone,
thing.
yeah.
Okay.
Or some type of wearable, your
Okay.
smartwatch.
Right.
How many people have smartwatches?
I
You got a
have
couple?
one.
Okay.
It's sitting at home because it sucks and I never use it.
Yeah, I have one, but it's sitting on my desk.
I should have to charge it every night with the phone. It's like it's ridiculous. And you can't really do much with it. It's pretty stupid.
I actually really like mine. The only reason I don't use it is because my phone is 3 years old and I don't want to have Bluetooth on all the time. My
Oh,
phone-
yeah.
My phone just drains so fast.
I found out they make ones that have custom interface that look like James Bond 64, so I might actually pull it back out just for that reason.
Okay, so it looks like we're still going to have this this competition between the different mobile and PC, but notice that the PC and the mobile are different domains. Most of your mobile devices are using an ARM-based chip, which is a very different architecture than x86, which is pretty much what all your laptops are using nowadays. Unless someone has a really old Mac, which I don't see, so everyone's x86. All right, so the book, I'm only mentioning this because the book mentions it, personal mobile device, aka your cell phone, and then we will go into cloud computing. Yeah, I don't have a very high opinion of cloud computing because you're just using someone else's computer, which is also just called server programming, which is what we've been doing the whole time, and now you're just going to rebrand it as cloud computing. Thanks, guys. But we will talk about it because you'll probably get to it at some point. All right, how programs are translated to machine language. That's what we're going to learn. How the hardware executes those instructions, the hardware-software interface. This is very important because we're going to talk about how we build hardware up to a processor, and then how do we have software that actually runs on it. We'll talk about the ISA, the instruction set architecture, and that is the hardware-software interface that we will get to. What determines program performance? This is actually, I've learned for some reason, students have the hardest time with this. So y'all can help me out. I don't know why, but this one we always have a lot of problems with. Of course, how can it be improved? How can hardware designers improve performance? And then what is parallel processing? And hopefully we will get into a little bit about that towards the end of the class. Have y'all ever done any multi-threaded or multi-process? Where did you do it? Oh, in OS. Who hasn't taken OS? Has anyone done any multi-threaded or
At the
multi-process?
very end of networking.
Networking? Oh, what'd y'all do?
Oh, yeah.
Yeah, we had to make a, what was the program we made? It was like a send and receive messenger.
Yeah.
And you had to make it be able to multi-thread so they could receive and send as two different threads.
Oh, how'd that go?
We basically faked it, so like it didn't really work, so we pretended it did, and he goes, because it was like, it was supposed to send a message back, so I just typed the message in, and he was like, look, it said that.
So, spoiler alert, this is really hard. People have been studying this for decades, and they haven't come up with good solutions in the end. I know, what a bunch of losers. But how are you going to take advantage of what was it? How many cores were in that thing? 2.5 million?
A lot.
A lot. How are you going to take advantage of 2.5 million cores, Brian?
2,414,592.
Oh my goodness.
$592.
Yeah, exactly.
Why not just line them up so they're parallel to each other?
Yes, but they all have to communicate to each other, right? And I mean, that's just like saying that if you have a problem, we'll just add more people and that makes it go faster, right?
It's true.
Every time, right? That was sarcasm?
That's what the military does. It works really good. It's directly proportional. The more people, it'll get done like half as long each person you have.
Yeah, but how much overhead is there in the military?
Nobody stands around and like watches the one person work while there's
Wow.
10 people.
All right. A couple of high-level things to keep in mind. There's the 3 P's of performance improvement. There's parallelism, aka running multiple things at the same time. There's pipelining, which we'll get to. That's lining them up in a pipeline in order to take advantage of, while you're working on one, you're really working on another part of the previous one. It's a type of parallelism, but it's usually separated out because of how commonly it's used. And the last one is prediction. So parallelism, try and execute multiple things at the same time. Pipelining, try and line them up so they execute faster overall. Prediction, if these two things don't work, the prediction is, well, let's guess what the result is and go with it and then find out if we were right or wrong later and then fix it up later. I'm not joking, that's what we do. No joke. Number 3 happens all the time.
It's like Google Stadia.
Yeah, exactly. Exactly. And if we're wrong, we'll just try and fix it. That's exactly what we do. Another thing, small is fast, big is slow. All right? That's how life is. Something is a small structure, it's going to be fast. If it's a huge structure, it's going to be slow. Very common. One of the biggest issues students have with this course is you have to start thinking in parallel. When you have a circuit, you have to realize that everything on the circuit is happening at the same time. And so it's not like a program where you execute. You have all these gates, they're all happening at the same time, and you have to think about how data will flow through the circuit to the end. So that's usually the biggest sticking point, so hopefully we can jump through that. We will be using Verilog, different type of it's a language used to describe processors. Since it's working in parallel, things are going to operate very differently than they will in C. But we'll get to that as well. Okay, about me, a couple people haven't, had a course with me. Real quickly, PhD from Florida State University in computer science, namely in computer architecture, so here I am. Yeah! Faculty experience at Charleston Southern since 2015, a couple of semesters at College of Charleston. Work experience, I work part-time at the Naval Research Lab, working on a lot of their security systems. I, of course, work on architecture as well as OS. I'm a systems programmer, so low-level stuff. I did work at Google for a year, so if you have any questions about that, feel free to ask me. It was a lot of fun, but I don't want to live in the Bay Area. I have worked at Spaywar for communications, and I did work at a startup for about a year and a half, roughly. I was employee number 7. That was also a lot of fun, but not good when you have family, since who knows what's going to happen with your job. So if you have any questions about that, feel free to ask. I use GitHub for all my assignments. Everyone here has had OOP? Yeah. Great. So it's going to work very similar to OOP, except for there's no autograder because it's kind of hard to autograde a lot of these things, as you'll find out. Fortunately, I don't have internet. Otherwise, I just sign everyone to GitHub right now. But please create a GitHub account and email me your username, and then I will email you back a link once I get back to my office, and I guess we're just going to have to do it that way. The other thing we're going to use is ScrumDo. Some of y'all have used ScrumDo before, others you have not. We will talk about it a little while, but the idea is that instead of me giving you assignments, we're going to have a board. We're going to throw cards up at the board, and I will need an internet connection to do this. So if I don't get internet soon, we're not using ScrumDo. But the idea is that you push your cards through a board, and then once you want me to review it, you put it into review, assign it to me, and then I'll go in and add the card and tell you if you did it right or not. And if you did it wrong, I send it back and tell you what you need to do. So think about that. That's very different than what you've been used to so far, because you're used to just getting a grade and it's done. In this case, I can kick it back and tell you to redo it until you get it right. One, don't take advantage of that. Do it right the first time. Otherwise, I will just start throwing them over to you did this wrong and give you a few points. We will use it if it allows us to create enough users. I'm pretty sure we have enough users, but you'll need to log on to ScrumDo as well, and then email me your ScrumDo username. You can log in via GitHub from ScrumDo, and it'll create everything that way. Yes. Oh, good. All right, let's go over.